For this question, we have a series of spectra in order to determine the correct structure of a compound whose molecular formula is given. As we've done many times before in these problems, we know that our first step is almost always going to be calculating degrees of unsaturation. 2 times the number of carbons plus 2 minus the number of hydrogens, and we won't worry about the rest of the formula because we don't have any nitrogens or halogens. And divide that all by 2. And so we get 6 degrees of unsaturation for this compound. So from here we can start looking at what we find in our structure. First region we may look at is our 3000 to 3500 region. And we notice we have a very small peak up in the high 3000s. This is in the right range for an alcohol, but we know from doing many of these in the past that an alcohol will usually be a much stronger peak. So while this spectrum doesn't say to us with 100% certainty that there's no alcohol, we can be probably at least 95% certain that there's no OH in this compound. What we can also be certain of is this peak, which shows up at 1675. And we know that's right in the range for a carbonyl. So at this point, we can look at our 6 degrees of unsaturation and the fact that we have some sort of carbonyl in this molecule and go on to our proton NMR. Now the proton NMR, especially for a molecule that has 10 hydrogens in it, may be a little bit surprising. We only have 2 peaks here. Both of them are singlets. But that does still give us a lot of information about this molecule. It tells us, based on this peak being around 8 ppm, we almost definitely have an aromatic ring. Now we probably guessed that we had an aromatic ring based on the degrees of unsaturation that we previously calculated, but now we can be even more certain of that. The second thing our NMR tells us is that this molecule is highly symmetric. Again, that's a reflection of the fact that there's only 2 peaks in the entire spectrum. The last thing that we can get from this spectrum is this peak here around 2.5 ppm. And while it's not exactly in the range, we do know that's pretty close to the range for a methyl group that's next to a carbonyl. And given that we just saw from our IR spectrum that we had a carbonyl, again, it's fairly likely that we're going to have that piece of the structure. So let's look at our carbon spectrum. Our carbon spectrum shows us 4 peaks. Again, very small number of peaks in relation to the 10 carbons we have in our molecule. But we see now 2 aromatics. So again, we know our aromatic ring has to be highly symmetric. We see what looks like a methyl at the end of some sort of chain, but next to something slightly electronegative. So that means that methyl is either going to be attached to an aromatic ring or it's going to be attached to a carbonyl. And then we have what's clearly a ketone or aldehyde peak, but we know in this case it has to be a ketone. If this had been an aldehyde, then the aldehyde would have shown up in the proton NMR around 10 ppm. So we'll start with our aromatic ring, and that accounts for 6 out of our 10 carbons. Now if we assume that there's a ketone in this molecule, we'll put that on the aromatic ring. And then based on this CH3 peak, we'll assume that it's a methyl ketone. Now we've accounted for 8 out of the 10 carbons in this molecule. We have 2 to go. We've also accounted for 5 of our degrees of unsaturation. And while it appears we may have another number of other options, we've said repeatedly, based on the proton NMR as well as the carbon NMR, that we know this molecule is highly symmetric. So our best option right now is to put another methyl ketone exactly opposite on the aromatic ring. What that means is that when we look at the aromatic ring, these 4 carbons will all be the same and give us one aromatic carbon. The other 2 aromatic carbons will also be equivalent and give us a second aromatic peak. So we've accounted for the symmetry, we've accounted for the functional groups, and we have our 6 degrees of unsaturation based on the aromatic ring as well as the 2 carbonyls.